Today we are going to show you how to send the model from Tekla Structures to Diamonds and synchronize it back to Tekla thanks to BIM Expert software. This is the model to transfer. It's a simple steel frame with columns IPE, girders IPE 140. The trusses are in HEA and 140 and 100 section. The columns in front on the other side, that is over here, are in HEA section. And we also see some wind braces. These have an angle, a corner section, so an L50 to 5. The material of all elements is S275. We have created an analysis model from this real-life model, and we can find it over here in the menu Analysis and Design. We even have created 2 analysis models, so let's take a look at the second one. The analysis model is a necessary first step in order to transfer the model to Diamonds. You might think, why exactly do we need an analysis model? Well, a real-life model, a physical model like in Tekla, does not equal the analysis model. Analysis model usually only consists of the axis of the elements, making them different from a real-life model. So at some point in time of the process between modeling and structural analysis, you need to schematize the real-life model into an analysis model. Analysis models can be created directly in the structural analysis software, Diamonds for example, or they can be created in Tekla Structures. And this is for transfer to a structural analysis software such as Diamonds. Let's take a look at some points of interest of this analysis model. The analysis model consists of the axis of the bars, and these coincide as much as possible in one node. Let's take a look at what's happening over here. If you would close the analysis and design models, you would clearly see that not all bars would meet in one point in the real-life model, but in the analysis model they do meet. And this is really essential for the analysis model. The analysis bars do not necessarily coincide with the neutral axis of the physical element. That's what you see over here. But for example, we have another one. If we take a closer look at the columns over here, we see that this column, the outer column, has a smaller cross section than the inner columns over here, but these are aligned on the outer flange. This would result in different positions of the analysis bars if we would strictly stick to the neutral axis principle. But allowing the analysis bar to be anywhere within the section, we can also keep the analysis bars neatly aligned. How to make this analysis model is treated in another video, so be sure to check our YouTube channel. With this knowledge of the analysis model, we are going to transfer this model now to Diamonds using the BIM Expert software. I'm going to close the Analysis and Design dialog. Now you can either click the BIM Expert logo or the Diamonds logo, but both serve the same goal: pushing this model into Diamonds. So I'm clicking the BIM Expert logo to send this model to Diamonds. And yes, we want to export an analysis model. And at this point, BIM Expert is taking over. He's asking me Do you want to transfer model 1 or model 2? So I'm going to transfer model 2. Now, currently all the materials, cross-sections, geometry is converted into a neutral file format. We also get a visualization of how does the BIM Expert software see the model that is loaded into BIM Expert, and it seems to be it's quite alright. So I'm going to export this to Diamonds. Now we have two possibilities over here. Either you can save it to a Diamonds file and then you can send this to a colleague or open it in Diamonds or put it on another machine, whatever you prefer. Or you can also send it to a Diamonds instance which is already open, and I just mean by that I have over here the Diamonds program open. I can send it directly to the open version of the software. So I'm going to do that. And okay, let's go back to the BIM Expert. As you can see, the model is gone and there's nothing in Diamonds happening. Well, you might think that at first, but of course there is something happening. We have on the right side, we have a notification bar. When I click this over here, you see that we have received a model in Diamonds and we can load this model. So I'm going to close now the notification bar. We won't be needing this anymore. And as we explained before, this is the analysis model, the structural analysis model, which purely consists of the axis of the elements, which is a simple line, a simple bar. But when you double click one of these elements, you can clearly see that there is information attached. So we have a cross-section attached, we have material attached, and so on. So indeed, for the columns we had an IPE profile. And the columns in front were an HEA profile, and we have the wind braces, which are an L profile, and a corner profile. We have the girders, IPE, we have here the trusses, HEA, and so on. So everything is nicely transferred, and on top of that we also have the supports. We have already defined them in Tekla Structures, and they were transferred also to the Diamonds. What is also important, well, if you look at the hinges at the end of the bars, these were also defined in Tekla Structures and are transferred, as so is the behavior of the wind braces, and wind braces are configured as a tie rod. That means it can only take on tensile forces. And as you can see, if you zoom in a little bit, all bars coincide or meet in one and the same node, which is the aim, of course, of a good analysis model. Having the model now in Diamonds, and we have checked some cross-sections and materials, you also see that different elements have different colors in Diamonds. These correspond with types. This is like same principle as layers, and you can easily select elements of a certain type with the control button. So it means holding the control button down while you click one of these elements, and all elements of the same type will be selected at once. So you can create your own types if you want, just by selecting an element and go to design types. Due to the fact that we have properly defined the boundary conditions in the Tekla analysis model, such as the supports and the hinges and the tie rods, our work in Diamonds is limited to adding loads, secondly performing an elastic calculation, Number 3 is doing a steel verification, and then also steel optimization with possibly adjustments of the cross section. And finally, we can return to Tekla Structures with a new cross section and synchronize both models. Let us start with adding loads. This is done in the loads window. So currently we are in the geometry window and we move on to the loads window. Adding loads and diamonds is done in 3 steps. First, we need to define the load groups according to the correct design standard for loads. Then we are going to add loads to the structure. And finally, we will make the load combinations. We define the different load groups over here. The design standard that we will use is Eurocode or EN. General version, but for example, American code is also a possibility. Depending on where the structure will be, you can choose the correct national annex over here. And the design standard will set the correct safety factors and combination factors. So it's important to choose this right. In this example, we will have 5 different load groups. First of all, being the self-weight, which is already present, and then dead loads, snow, wind, and seismic. And let's add these 4 other load groups. And when you add a load group, it's important to choose the correct load type from the pull-down list. So the first one is dead loads. It's important because the safety factors and combination factors will be set automatically. Let's see this happening again. So adding a load group, everything is set to 1. Now when we choose, for example, snow, these are modified according to Eurocode. I'll add another load group, which is wind, and another one, which is seismic. I'm just going to consider one case for the wind load because it's just a simple example, but in a real life project, of course, you could consider wind from left to right, from right to left, from front to back, etc. And we click OK to confirm. Let us now add values to these load groups. Well, the self-weight is calculated automatically because all cross sections and materials were transferred from Tekla Structures. No work to be done here, so we move on to the dead loads. We will add a dead load to the roof of 0.11 kilonewtons per square meter. This is easily done with a surface load generator for bars. First, we select all the roof girders and let's move on to a front view. We select them like this, and we will keep only these ones visible. And now with the control button, because it's a design type, I'm selecting only these ones. And in the top view, let's choose only these. So we end up with this selection, which was the aim. And we have now this button visible, surface load generator for bars. And we are going to add a vertical load, and you see these 3 little icons. These icons will change depending on the orientation of the model, so you can be sure that these are okay. And we want a vertical load, and the arrows are pointing downwards, so that means we can enter a positive value, and I enter 0.11 and we hit OK. That's for the dead loads. Now let's move on to the snow. And for the snow, I will use a snow generator, which is built in Diamonds. You can also use a value over your own with a surface load generated, just as we showed for the dead loads. First, we define the snow load, and we do that over here in settings. The snow will be according to Eurocode, and it depends on the area, the zone, and the height above sea level. On a real project, you would select the national annex from the list over here. So as I haven't chosen one before, I won't do it now, but of course you should for a real life project. Now we choose Central West for the zone, and we choose Area 1, and we set the altitude to 5 meters, and we click OK. Still having the girders selected, I can now apply the snow for groups of bars. And the only thing you need to define over here is the correct load group, snow of course, and the shape coefficient and the shape factor. For a roof up to 30 degrees inclination, this factor mu is 0.8 according to Eurocode. And we hit OK. We move on to the wind load case, and I'm going to show the whole model again, and we are going to add some wind loads on the columns only. So I'm going to keep the control button down and click once on the columns and keep only these elements visible, and we will define a wind load going from right to left. So selecting all these elements, and I'm going to use the surface load generator again. Here we need to be careful as the wind is going from right to left. I'm selecting this one in the Z direction. However, the arrows point in the opposite direction, and I want it from right to left, so I need to add a minus 0.8, and here we will add again minus 0.4 for the leeward side, and we have defined 0.8 for the windward side. And you can create multiple cases for the wind, also from left to right, and so on and so on, but just for this example this is enough. And finally we go to the seismic load group, and we will show all elements. We will add a seismic hazard according to Eurocode 8. Here we are. The ground type is 2. The important class for the building is standard, and standard class is 2. So that means we have a safety factor of 1 that is used for dwellings, houses, little steel structures, etc. The behavior factors are taken 1.5, 1.5, 1.5, and the ground acceleration is set to 0.35, and we hit OK, and we see this one appearing, meaning that we have defined a seismic hazard, seismic action. So we have completed already 2 steps in the load definition, so making the load groups and adding the values to the load groups. Final step over here is making the load combinations. For load combinations, we move to this button over here, and you can perfectly create your own load combinations, but the easiest way over here is just creating all combinations automatically. and we do want to see the individual load cases. So that means we can see the deformation and the bending moments for self-weight, for dead loads, for wind, and so on. We also want to see the ULS, the ultimate limit state fundamental combination. Also the seismic combination, which is important because we've added seismic action. And then we will take a look at serviceability limit state, the rare combination. So the ultimate limit state combinations will be used for the evaluation of internal forces, strength and stability. And the serviceability limit state, this one over here, will be used to check deflections, vibrations. I click OK. And here we have the different individual load groups, and then we have all ultimate limit state combinations and serviceability limit state combinations. Now we are ready to launch the elastic analysis. This is done with a little calculator over here. Now, before we see the analysis parameters, Diamonds asks us to choose a mesh. Well, don't forget that Diamonds is a finite element method software. That means in order to be able to calculate any structure, it first needs to be chopped up in little pieces. And for these little pieces, we do have a calculation method. So you as a user, you need to set the number of divisions for each bar. And 8, the current value, is perfect. In the analysis settings window, we choose a first order analysis. Strictly speaking, you should always perform a second order analysis. However, first order analysis is the first step towards a complete structural analysis, and second order analysis takes more time than a first order analysis. So we are going to choose over here first order analysis, and I click next. Now, as we have a seismic load, we also need to calculate some eigenmodes. We cannot calculate every eigenmode because there are infinite eigenmodes, and we are usually only interested in the lowest ones. So we set it to 10 to start with, and I launch the analysis with OK. We can now look at some results. We are automatically redirected to the results window. You can see it over here. This corresponds with this window. For example, the vertical deflection. This will be evaluated in a serviceability limit state. So let's move on to serviceability limit state, and let's have a look at the vertical deflection. And the maximum vertical deflection is 20.7. Now, bending moments, shear forces, normal forces would be verified in an ultimate limit state combination or envelope. So these are the bending moments, normal forces, and shear forces. And we can also consult the reactions and the stresses. In order to decide if the structure is okay, yes or no, we need to check 3 things. One is the stiffness. Now, this means it's deflection within the acceptable range. Each design code has its limits for the vertical and the horizontal deflection. It's up to the user to verify that the current deflection is allowable. Let's assume that the limit for horizontal and vertical deflections is span divided by 300. Looking at the serviceability limit state, the SLS, rare combination, vertical deformation, it seems to be okay. We have 5.6 span for the girders, and it's divided by 300. So let's take the calculator. So we have 5.6 divided by 300. Then we have something around 18-19 millimeters. We are currently at 20.6. So that means we need to do some little adjustments. If we look at the horizontal deformation, we are, for the X direction, we are at 4.9. And for the Z direction, we are at 30.4. Now this will probably be a little too much. Let's check. So we need to have the height of the columns. Let me take this one over here. Let's measure it. It's about 8 meters and a half. We can see this here. And this one, these columns are 9.32. So we have 9.32 divided by 300. We are at 31, 32, somewhere between 30 and 31 millimeters that we can have. So this is just allowable. So next to the stiffness, we also need to verify the strength. This means, can every cross-section of the structure take on the acting moments, shear forces, normal forces, and the combination of them? It means, has the structure enough capacity, enough strength? To verify this, we can ask Diamonds for a steel verification. And before we do that, I'm moving on to number 3. And number 3 is stability. This means, can every bar, so that means beam or column, can it take on the acting moments, shear forces, normal forces, and the combination of them? Is there a risk of buckling or lateral torsional buckling, or a combination of both? To verify this, we can also ask the steel verification, so it's quite a useful thing. Steel verification can be asked over here. Analysis, steel design code, we choose Eurocode. Of course, as we didn't choose one before, I won't do it now. So no national annex, but of course for the real life project, you set the correct national annex. Now for the strength part of the steel verification, so can the cross-section take on the bending moments, normal forces, etc.? Diamonds has all necessary input. It has the material, the cross-section, etc. But for the stability part, it will be currently based on the element's length as buckling length. This is of course not always correct. How you can modify this and how you can let Diamonds calculate the buckling length is explained in our manual. Let us launch the steel verification and we will look at some results. So this calculation is done, and when you double click bar, you can see the details of the verifications, and both ULS fundamental combination and the ULS seismic combination are checked. There are 3 interpretations of the result possible. Number 1, the result is a little less than 100%. That means that the current cross-section is okay. There are no changes needed. 2, the result is a lot less than 100%. So that means over here in our column, we are currently at 42%. That means 42% of the capacity of the strength, the resistance of the cross-section is used. So we have about 58% extra that is not used. In this case, it means design is not economical. We need to choose another, a lighter cross-section. But of course, you cannot base your conclusions just on this one bar. You need to look at all the girders, all the columns together to see if you can modify all girders or all columns or all wind braces, as you do not want to end up with 200 different cross sections. And the third one, the result is above 100%. That means that the current cross section is not okay. We need to pick a bigger cross section. So, strength-wise, this is the first icon over here. Everything seems to be quite okay. You might conclude that some cross sections are a little too heavy, so they can be executed in a lighter shape, in a lighter cross section. But you see, you need to evaluate together with the stability results. And here we can see in the stability check that some girders and some columns are loaded heavier than just in a strength situation. So you need to check both before you decide. And we have some bars even crossing 100%. So you should attend these and check what we can do. Whether you decide to modify certain cross sections, there are two possibilities. Either you use the optimization function in Diamonds. This is an automatic optimization function, so that means we can target, for example, for 100%, and we will optimize for strength, resistance and stability. And then on adjusting the cross sections, we will ask a summary and confirmation of what has been changed. And of course, there's some interesting stuff over here. Equal cross sections remain equal after optimization, which is quite handy. Otherwise, you end up with, again, 300 different cross sections. And what will happen over here in the optimization process, as all our sections come from library, that means an IPE or an HEA, you will see that Diamonds will look within the IPE or look within the HEA library to find a better cross section for which the resistance and stability comes closer to 100%. So this is one possibility to use the optimization function in Diamonds. Another possibility is that you just go back to the geometry window. You select, for example, this column. You open the section library and you choose another profile and modify all the sections that you want, and then you just recalculate everything. Another thing we can do over here is add some elements. For example, maybe we decide that 30 millimeters horizontal deflection is too much really, and we want to limit this. So how could we do that? By choosing, for example, bigger columns, or we could add wind brace, and that is exactly what we are going to do right now, is adding wind brace. So I'm going to add some bars to the model. And while you are drawing, you can just zoom in and out. And the reason why I want to show you this is because these elements will be transferred back to Tekla Structures. here we are. And for the cross sections now, well, I'm just going to do click right mouse button, copy properties, and with the control button I can select all new elements and paste the section material and type. Only thing I need to say over here that, listen, this is a tie rod. Okay. What else could we do? Well, assume that you might want to change a certain column section. You could, for example, modify this one, and instead of 240, we will choose 220 cross section. And another interesting feature, and this is purely for demonstration purposes, I'm going to show you this. I'm going to edit the position of one of the girders. So I'm copying this one. I'm copying this one from here to halfway over there. Take one copy, okay, and going to delete this one. So the original girder does not longer exist, but I've created a copy and it's now over here. So let's assume that we have rerun the elastic analysis and everything turns out to be okay, and we are happy with the cross sections and the materials and the geometry and whatever. And now we want to go back to Tekla Structures and synchronize our changes. How do we do that? Well, we go to File, Export, Export to BIM Expert. And now, apart from the new elements and the modified column, we also see that the BIM Expert is alerting me that we have some kind of conflict, and apparently bar number 161 has moved. Now, as you can see, this is showed here in white, and we can choose to accept it, to reject, keep the physical elements, or also discard the physical element. So you see that the new one is over here, but the BIM Expert is recognizing what, oh, this one is gone. Is the new one a replacement of the old one? And this is of course not so easily decided because the position has fundamentally moved. It's not just a couple of millimeters. I move it at over 1 meter. And we do want to accept the changes, and we click OK, continue. This is the new model, and as you can see, the new model has this girder over here, and we will export this, and we will now synchronize it with Tekla Structures. And the version that I've used to make this model is the 17 version, but I have different versions installed on my computer. So export. How should we treat the analysis models? Well, we can export a new model to one of these two, or we can create a new analysis model, or we can create a copy of the selected analysis model, and I'm going to do that, and I'm going to call that model 3. Okay. And now all the diamonds information is translated to Tekla materials, Tekla cross sections, Tekla positions, and so on. So this takes a little while, this step. Now we have another question popping up. Do you want to set up the models in insertion data? So that means, do I want to choose a new point of insertion for this model? No. I want it to be inserted as it was before on the original position. Whether you want to insert a model elsewhere than default original position, click yes if you want to insert a model elsewhere, and here the original insertion point is where the current physical model is located, and we want to keep this, so let's say no. On returning to Tekla Structures, we get a dialog window informing us of some new parts, and of course, remember we've added some wind braces. These are the new parts, and when you click them they become active and you can see where they are located, and you can choose to accept them, yes or no. And then we have some parts with changes, and the main part over here, or the main changes, is the column which has changed from an IP to an IP 240 to an IP 220, and the rest are just orientation changes which is inherent to the analysis model. You can choose to accept yes or no, and when we hit OK, the model will be rebuilt. So here we are. Let's look around. What we can see over here is clear that this girder has moved, the position has really moved, and we have additional wind braces. These are not in the correct classification yet, but they are added correctly to our physical model, and with the correct cross section, of course. We have come to the end of this video. We have shown you how to go from Tekla Structures to the analysis software Diamonds with the help of the BIM Expert software. And in Diamonds we've added load groups, we have performed an elastic analysis, and we have returned to Tekla Structures with synchronization of both models. I want to thank you for watching. I hope to welcome you again at one of our next sessions. Don't forget to subscribe our YouTube channel.